Hello and welcome to Calculus Tutorial. We are now again looking back at relative extrema. So we took a look at absolute minimums and maximums. We're going to go back to relative extrema, which is just any hill or any valley. And the way we did that before was with the first derivative test and your sign chart, and you look to see whether the derivative is going from positive to negative or negative to positive, and that tells you if you have a minimum or maximum. Well, there is also a second derivative test, where instead of using the first derivative as your logical source, you're going to use the second derivative. And this test does the exact same thing as the first derivative test. As you can see, they both find relative extrema. They just use a different logic to do that. So we're going to start by doing this analytically with an equation. How can we use the second derivative to find a minimum or a maximum? So we have this equation here, and we're going to use the second derivative test to find minimums and maximums. I think we used this equation once already. But you start out doing the same thing. You start out by taking the derivative, the first derivative. So that will give us x squared minus x minus 6. And you still have to find the critical points by setting this derivative equal to 0. Okay? So if we factor this, you will get x minus 3 and x plus 2. And so our two critical points are positive 3 and negative 2. So each of these are either relative minimums or a relative max. One or possibly neither, I suppose. And what we did last time was we did the sign chart, and that sign chart is technically the first derivative test. What we're going to do is the second derivative test, and that just again determines whether this one is a min-max or neither, or whether this one is a min-max or neither. But instead of using first derivative logic, we are going to use second derivative logic. Alright, so what is our second derivative? It is 2x minus 1. And what you do is you take the second derivative and you just plug in the critical points. So we're going to plug in 3. If I plug in 3, we get 6 minus 1 is 5. Now what does that tell us? Well, over here, I'm going to draw our 3 graphs again. Okay? Well, if we have a maximum, the first derivative test tells us the derivative is going from positive to negative, and with a 0 in between. And if we have a minimum, then we know the first derivative is going from negative to positive. Well, how can I interpret that slightly differently? Well, if you're going from 0 or from positive to 0 to negative, that's decreasing. And if your derivative is decreasing, that means your second derivative must be negative. Let's take a look at the minimum. If we're going from a negative to a positive, to 0 to a positive, that's increasing. You're going up, which means your second derivative must be positive. Another way to think about this is if your second derivative is positive, positive 5, your second derivative is positive. What does that mean for the original function? That means concave up. So think about that. I know that this, x equals 3, has a slope of 0. It's a critical point. So here's my slope of 0. But now I also know it must be concave up. Well, the only way to draw a concave up graph is like that. And so we now know that this must be a minimum. Okay, f Let me rewrite that. I'll actually put the function at 3. F at 3 must be a minimum, a relative min, because, and then we'll do everything. The first thing I know is that f prime at 3 is equal to 0. That means we have a flat spot. And f double prime at 3 is equal to, now I could put 5. I don't really care about the 5 so much as that it is a positive number. So I'm going to even put the plus there. All right, which means the graph is concave up. Okay. I'll even add that. I probably don't need to add that last bit, which means f is concave up. At x equals 3. And let's do the other one. I only have room down here, so f double prime at negative 2. So if we plug in negative 2 times 2 is negative 4, minus 1 is negative 5. Alright, so this means our graph is concave down. We know we have a flat spot, but in order to draw a concave down graph, it has to look like that. And so we know that this one will be a max. And so I'm not going to write that sentence, but you could write a sentence very similar to that one to justify this conclusion as well. So instead of doing the sign chart, you simply plug into the second derivative, and whether that value is positive or negative will tell you whether you have a minimum or a maximum using concavity. Just a different type of logic to come to the same conclusion. Alright, now there's one other way you might see that, which it looks more complicated, but there's actually less work involved. And that is if you're not given an equation. Okay, so we did it analytically. Sometimes I can switch this up by giving you a table of values instead. So the following table represents information about a function's first and second derivatives. Use the second derivative test to determine relative extrema for g of x, the original function. So we just want to do the exact same steps as last time. Last time, the first thing we did was we took the derivative. Well, hey, look, it's right here. Then we set that derivative equal to 0, and we solved the equation. Well, take a look. Here the derivative is equal to 0. What is the x value? Negative 2. So when you plug in negative 2 to the derivative, you get 0. It actually happens one more time right here. So we solved the derivative equal to 0. Hopefully you can see that's easier because there's no actual solving that you have to do. You just have to look up the information on the table. Alright, what did we do then after that? Well, we took those two values and we plug them into the second derivative. Well, so if we plug in negative 2 into the second derivative, we get 0.17. And if we plug in 0 into the second derivative, we get negative 0.5. Now the number we don't really care about. It's only whether that number is positive or negative. This number is positive, which means the graph is concave up. So think about a concave up graph, and you can hopefully visualize the minimum. So g at negative 2 must be a minimum. And then if we think about this being a negative number, that means concave down. which means this one will be a maximum. So g at 0 must be a max. So there we mostly just have the logic and not the actual solving or the analytical taking of derivatives with the equations, but the logic is the same, and then you would still want to be able to write the justification sentence. So how do we know that g at negative 2 is a minimum? G at negative 2 is a relative min because g prime at negative 2, the first thing we found out is that g prime at negative 2 is equal to 0, and g double prime at negative 2 is positive. And then you could write a similar sentence as well for g at 0 being a maximum. So again, this does the exact same thing as the first derivative test. It finds minimums and maximums, but it uses a different type of logic. Instead of using increasing and decreasing language with the first derivative, it uses concavity with the second derivative. But as you can see, it still accomplishes the same thing of finding relative extrema.